Hey there. My name is Eric Burketto. I am a generative AI software engineer and an open source intelligence researcher. And today I'm excited to be presenting to you my recent capstone project called T.S.G.P.T, or Trust and Safety GPT. This particular project is a multilingual extremism detection and content moderation system that is designed to reproduce Meta's own content safety mechanisms for detecting harmful speech and content and enforcing against harmful content and mentions of dangerous individuals and organizations, also known as DIO or sometimes DOI. I built this particular project as part of a capstone project spread across two different advanced LLM application building courses, building LLM applications from scratch and advanced LLM application building, the latter of which I now have graduated from being a student to co-teaching as a teaching assistant. In this particular project, as I mentioned before, this is all built around Meta's dangerous organizations and individuals' capabilities and how it integrates its own policies for DOI into its existing content moderation systems. So let's dive into it. The core problem that I'm tackling with TSGPT is the challenge that modern platforms face in effectively moderating extremist content. This kind of harmful content often glorifies dangerous individuals and organizations, posing real-world threats to community safety, both online and offline. To address this problem, I built TSGPT as a prototype system that not only detects and classifies those sorts of extremist contents, but also enforces policy-driven moderation actions in order to maintain platform safety. Essentially, the project aims to model and enhance the detection and enforcement capabilities that we see at so many leading social media companies like Meta and Facebook and Instagram. My main goal here is to create a system that is capable of handling multilingual content, making nuanced decisions based on predefined policies in a policy-driven content classification setup, and maintaining a balance between community safety and freedom of speech. Now, in terms of the system architecture that I used for building this application, let me take you through that here. First, we have the Neo4j knowledge graph, which is storing the dangerous organizations and individuals list from Meta, essentially mapping these entities' aliases and relationships. I enriched the publicly available list of Meta's DOI using the diffbot knowledge graph data, which makes it robust and capable of handling multilingual entities. Second, we are using self-hosted LLMs in an LLM API server in order to handle named entity recognition, sentiment analysis, and the enforcement decision-making, which keeps the architecture efficient and cost-effective. And then finally, in order to handle the overall data flow in the application layer, I implemented the Hamilton DAG framework, which allows me to build modular functions in a directed acyclic graph for each step of the pipeline. Each component is then handled as a modular task, which enables us to have a highly organized and scalable architecture. And then the actual data sources that we used, as I mentioned before, is not only Meta's Dangerous Individuals and Organizations list, at least a publicly available one, and enrichment of additional fields like multilingual aliases from the diffbot knowledge graph and their natural language enrichment API, but also a dataset called MIWS, which is a multi-class, multi-labeled dataset of short extremist texts, which is published in an academic research paper several years ago, where the texts were written by and collected from Islamic State Salafi jihadists from several magazines that were published by ISIS, as well as Western white supremacists. Now, when we move into the radicalization detection step, the overall challenge here, remember, is to be able to identify and flag messages that are promoting extremist ideologies. In order to do that, I built the embedding pipeline, which is run against the MIWS dataset once it has been converted into vector embeddings, And this pipeline calculates semantic similarity between input text and these known extremist texts, this known extremist content. This pipeline uses the semantic similarity with the hierarchical navigable small worlds graph algorithm to predict what ideology is in the input text if it scores high enough to be classified as extremist. It's given either a label of white supremacist ideology or a Salafi jihadist ideology. And in addition to that, the semantic similarity process also classifies the message based on the type of radicalization communication appears to be inherent in that message. For example, recruitment or propaganda or just straight radicalization. I used Hamilton for this entire tech stack, as well as the face in-memory vector store with a library actually released by Facebook for vector searching, along with embedding models from OpenAI and semantic similarity. Then we have the knowledge graph, the enriched knowledge graph that stores the dangerous individuals and organizations. Here is a preview, a screenshot of what the underlying knowledge graph now looks like once it has been enriched and ingested into Neo4j. You can see here we have our knowledge graph of organizations that have been linked to the hate policy category. You can see also that we have selected and previewed the Aryan Nations organization node there in the middle of the screen. You can see on the right the list of enriched properties that we have obtained using the original name of the organization from Meta's Dangerous Individuals and Organizations list, and enriched with additional properties from the diffbot knowledge graph, including, most especially for our purposes, the all names property, which contains the list of all aliases across multiple languages by which the Aryan Nations organization is known. Okay? With that Neo4j knowledge graph in place, we can then move into the multilingual detection and classification to detect the mentions of these dangerous organizations and individuals in a multilingual capacity. The process for doing this involves integrating of a couple of different large language models. We have the universal NER, or named entity recognition model, which handles the multilingual NER to identify peoples and organizations mentioned in the text, regardless of what the underlying language is. Then we have the Neo4j full text indexes that have been added into the knowledge graph in Neo4j. There are several different indexes for several different language groupings that have been set up in order to handle diverse alphabets, in order to be able to provide accurate identification of DOI entity mentions. Then we have the sentiment analysis, which if a message is classified as mentioning a DOI entity, well, the sentiment analysis then comes in and classifies whether that text is expressing sentiment that is glorifying or supportive of that entity, which would be a violation of the community standards and platform policies, or if it is expressing a neutral or a negative sentiment towards the DOI mentioned entities. The actual tech stack that we used for this is, again, the Uni-NER model, the 7B model specifically, and the Mistral 7B model, both of which are quantized. These two models are served in a fast API server on Google Colab GPUs using ngrok for doing the network tunneling from the Google Colab environment to a local or a Hugging Face or other API serving setup. Then again, we have the Neo4j AuraDB, the managed cloud-based AuraDB for the graph database. We have the Hamilton DAG library for implementing the modular data flow and the interaction between models. And then we are using FastAPI and Gradio for the actual application server of this content moderation system. Once extremist content is detected, it's essential for us to decide how to respond to it. And this is where the policy enforcement mechanism with its own dedicated endpoint comes in. The enforcement process begins with classifying the violation type, such as the hate speech or the terrorism, based on the detected content and the policy of violation that the entity is assigned within the knowledge graph. The system also considers contextual inputs, such as the user's age or history of past violations, in order to refine the enforcement decision, as well as the nature of the message that is mentioning the actual DOI entity. Using these inputs, the enforcement mechanism can then generate tailored actions, ranging from warnings to content visibility reduction, or even more severe penalties like account restrictions or permanent banning. The goal here is to create enforcement options that align with the platform's guidelines, so that we are ensuring user safety without unnecessarily stifling freedom of speech. Some of the key technical achievements of this T.S.G.P.T project include building a complete end-to-end detection and moderation pipeline that integrates multiple NLP and LLM components into a cohesive system, with a setup that allows us for dynamic and scalable content moderation in a production-style way. It gives us high flexibility and scalability because of our use of the Hamilton DAG library, which makes the system easy to scale or modify. And that means that adding new data sources or expanding detection capabilities can be done efficiently. Additionally to this, the policy enforcement logic stands out here because it provides customized responses based on a user's behavior, based on the user's content, as well as our own written policies and community standards that then demonstrate the kind of nuanced moderation required to foster both safety and freedom of expression in online communities. Now, for the live demo, I'm going to be showing you the full moderation flow. However, I want to give a content warning here before we get started that necessarily the examples and input text that you are about to see are going to contain disturbing language that is specially crafted to deserve moderation and takedown. So, viewer discretion for these examples of the demo is advised. We'll take a look at the ability to predict the ideology of text and classify whether it is extremist or not extremist. For example, if we pass in user input text that says something like, for example, the Nazis, nothing wrong, we get back a prediction that this is indeed extremist text with the white supremacist ideology, and it has been classified as an example of propaganda, specifically. Similarly, if we replace this with an example such as, if you want to fight for the caliphate, DM me, and we submit this, we get back a classification of extremism under the jihadist ideology, which has accurately classified this text as an example of recruitment. Now we can test to make sure that the entity mention and glorification detection function works as intended. If we go back and take one of our previous examples and tweak it a little bit to, for example, Joseph Mengele did nothing wrong, and we submit this, we can see that Mengele was detected as an entity mentioned in the text that exists in the Dangerous Individuals and Organizations knowledge graph, linked to the hate policy category, and the entity recognition combined with the sentiment analysis, the aspect-based sentiment analysis, accurately classified this sentence as expressing glorification of this particular entity of Mengele. Of course, it is always important to make sure that content moderation systems are finely and thoughtfully tuned so that you minimize the rate of false positives, because false positives in content moderation ultimately damages user trust on the platform just as much as too low of rates of true negatives. So, if we change this example to an example that is instead still mentioning the same dangerous entity, but in a neutral or negative sense, we should expect that this content will not be actioned upon by the system. So if we change this to something like Mengele did some of the most atrocious and heinous acts in World War II, and we submit this, we find that it has been scored with a negative sentiment towards Mengele, which is precisely right, because this is a condemnation of the mentioned entity, not a glorification or an expression of support. Likewise, if we change it to something more fact-based or news coverage-based, such as this neutral sentence, which is a statement of biographical fact, and we submit this, the content is classified with a neutral sentiment, which means that it would not justify actioning and enforcement of community standards, thereby protecting freedom of expression and the ability of users to be able to discuss dangerous entities in a neutral and condemnatory manner, and thereby enhancing users' trust in the overall platform. Now, if we take this output and we go to the Policy Enforcement tab, we can then submit this output for a decision about how to enforce on this given message. So if we go over here and we paste this in as a next step in our orchestrated call of these two API endpoints, and we submit this, we find that the system has recommended a temporary suspension for the user who posted this particular imaginary message here. The reason why it does so is precisely because it is directly glorifying, in this case, a notorious figure associated with violence from the World War II and the Third Reich, which is a violation of this platform's community standards. So a temporary suspension would allow this user to essentially reflect on their behavior while also making sure that we are minimizing any harm to our platform's community as much as possible. Now let's take a look at a series of other examples to test how this functionality between the two endpoints works for other organizations and other languages as well. Finally, let's look at the potential future directions for T.S.G.P.T, as well as some of the lessons that I've learned from this project along the way. In terms of potential enhancements, I see a few exciting opportunities here. One direction that we could go is to expand the detection capabilities with more sophisticated mixed language analysis and classification of different forms of sentiment and different types of violative content. By integrating advanced caching strategies, including some semantic caching, we could improve the overall system performance, whereas we also have the option to incorporate a wider range of models, including vision language transformers or computer vision models, which would then allow the system to detect extremist imagery alongside text-based content. And additionally, I can add an active learning mechanism, such as continual pre-training on top of fine-tuning, in order to keep the models updated and responsive to evolving threats from online communities. As for lessons learned, this project has really underscored the value of combining graph databases and LLMs for flexible and dynamic content moderation. It also emphasized the importance of balancing technical complexity with the safety requirements of both users and the platform itself. So creating a moderation system that's both robust and adaptable is a significant challenge, but it's one that I'm deeply committed to tackling. Thank you for watching, and I hope you found this project as inspiring as I did. And if you'd like to learn more or discuss this work further, please feel free to reach out.